Greetings. Today I'm going to be talking to you on mechanics of materials, axial video number 2, and the title of the video will be the stress strain diagram. So, as we talked last video, we've got some object loaded in some way along its primary axis. We call that axial loading. And again, we typically talk about the force in terms of the symbol P, some sort of cross-sectional area A. The material is made out of something, plastic, wood, steel, aluminum, and it has its own E, modulus of elasticity. And it started with some original length, ended up at some final length, where the difference between the original length and the final length is delta. And we can actually calculate delta if we know P and L and A and E. We also talked about stress as being P divided by A and strain as being delta divided by original length. So now we're going to plot for a given material stress versus strain. Stress on the vertical axis in units of psi, strain on the horizontal axis with units of inches per inch. And let's think about this in terms of tension. So if I have zero stress acting on our object, how much longer do you think it gets? Oh, it'd be 0. So, but if I start to put some stress on, will I start to get some delta? Yep. So I'll start to get some strain. So put on a little bit of stress, get a little bit of strain, a little bit of stress, a little bit of strain, a little bit of stress, a little bit of strain. And you end up with a straight line. And we call that straight line the stress strain diagram. Now, when you have a straight line, it typically has a slope. So back to 9th grade algebra, y equals mx plus b. Let's replace all these things. Well, what's the y-intercept? 0, so that can go away. And on the y-axis we have stress, and on the x-axis we have strain, and the slope is different for different materials. In fact, it is the modulus of elasticity. Stress is modulus of elasticity times strain. This equation of relating stress and strain is called Hooke's law. You may remember Hooke's law from physics, where we used it in terms of a spring with the force and the elongation and the spring constant. Same equation. So the relationship is the more stress you get, the more strain you get, and the amount of strain you get is going to be dependent on what material it is. As a civil engineer, I had used the modulus of elasticity for steel so many times that I even remember what it is here today. It's 29 times 10 to the 6th psi. That's a pretty big number. 29 million psi is what the modulus of elasticity is for steel. You can find various moduluses or moduli of elasticity in the back cover of our textbook, Average Mechanical Properties of Typical Engineering Materials, and there it is, steel, 29 times 10 to the third KSI, that's 1000 PSI, so 29 times 10 to the sixth PSI. Let's see, we also see titanium and magnesium and copper, cast iron, aluminum, concrete, plastic, wood, and then in the bottom, right there, same graph, or same table rather, but for metric rather than English units. All right, there it is, stress strain diagram. I'm going to open to the appropriate page in the book and show you some more details about the stress strain diagram. So right now I am on page 88 in our textbook, and this is the stress strain diagram for a ductile material. Ductile are materials that do stretch, whereas brittle materials have different shapes. I do encourage you to read some of the pages around this page, say from 87 to 90. This is unlike most textbooks, this one does have information that's relatively easy to read and understand. So I do encourage you to use this textbook as a resource. Okay, so back to the stress strain diagram. Again, we've got stress on the y-axis, strain on the x-axis. And here's the diagram the way that I drew it for you. We call this region the elastic region. Now, in the elastic region, when you apply a force to an object, it gets longer. When you take the force off, it rebounds to its original length. So you've got, again, it'd be elastic. It's beyond that, and you'll see these different limits, the proportional limit, the elastic limit, the yield stress, the ultimate stress, the fracture stress. Beyond this point, when you leave the elastic region, the material, due to the force that has been applied, has been permanently changed in shape. And I always use the slinky. When I had my first slinky as a little kid, I would stretch it, put it back, stretch it, put it back, stretch it, put it back. And then my little brother would stretch it too far and it wouldn't go back any longer. When he stretched my slinky too far that it couldn't return to its original point, it left its elastic limit. In structural engineering, which is where most of us mechanical and civil engineers use mechanics of materials, everything we do is in the elastic region. Now, when you take material science from Andy, if you have already or in the future, you will start talking about material properties where going beyond the elastic limit does have some positive reasons and some negative reasons, and the material science property reasons for what happens up there. But in this class, we just don't live up there. We don't design steel to yield. We design steel in a bridge, aluminum in an airplane, wood in our house to behave in the elastic region. So Hooke's law is valid down here in the elastic region, and this is where we'll spend most of our time. But knowing the stress-strain diagram is definitely a fundamental principle of this course. You will be expected to describe what's going on in the stress-strain diagram on the FE exam. So, there we have it. Stress-strain diagram. Over and out.